for the introduction. I want to thank the organizers for just decided to organize a meeting and to dedicate to the memory of one of my best friends and outstanding mathematicians. So I will talk about his work and his life. I will start my talk and I will finish my talk more or less like a Pink Floyd very famous LP, Dark Side of the Moon. I mean, I will start with something, I will just make a round and just come back to the first. On Saturday 2021, I was just sitting in my room at home. I was talking with one of my oldest friends was Petronilo, and we was discussing what will be our next project, mathematical project. He was very happy. He was making a lot of jokes, sarcastic jokes, essentially. He loved that. But he was very tired because in the last years, he could not sleep so well. We always made a lot of jokes, say that about that. And we never, I mean, even I never knew that it could be happen that it was the last time we meet together, at least virtually. Okay, the first time when we meet, it was in Leganés. I was making the PhD thesis with Professor Marcellan. He also, Marcellan tried to convince us to rent, say that a room for one of his students, and we didn't want to do it. And we argued a lot of stupid things like, what happens if this person smoke? What happens if this person, I don't know, is noisy? Somebody that knows Petronilo knows that this is the orthogonal to that, okay? But at the end, we did it, and he come. Okay, I remember exactly that was in the winter of 93, 94, maybe December or January, I don't remember exactly, and a little Ford Fiesta, red Ford Fiesta, arrived, a young man, very thin and shy young man, go out from the car and presented himself. I am Jose Carlos Petronilo. And this was with him, was his wife Celia and the brother of Celia, Fernando. They didn't want to go up because they need to come back to Sevilla, sorry, to Coimbra. It's a long trip. But Jose Carlos just stayed at home. I still remember that this day, for dinner, we just asked him to join us, and Jose Carlos told us that he already have a dinner in a restaurant close to their house. And so we were very, very hungry with him, and said that this is impossible, you cannot do that. Imagine, we didn't know to each other, and it was so embarrassing that after that, he never went out for eating in any place except with us. Say that these first days, we never knew that we became very close friends. Even the families were very close friends. I mean, I and my wife, especially I, because I travel more to Coimbra, I just was a witness of how their kids, the two daughters, grow up. Okay. Wait a moment. In this talk that is open this Congress, I will share with you a lot of remembering that I have. I mean, a lot, some of my rememberings, and also, of course, I will comment some of the mathematical, say that, results that he considered his most important results. Okay, here is a photo in working at home. As you see, a lot of books over there, and this is the last photo of Petronilo. 1 hour later on, he had a stroke, and he just could not recover, and he died several days after that, surrounded by his family and his closest friends. Okay, so let me go. I will divide my talk more or less in the following. I will just talk about the works on classical and orthogonal polynomials, works on polynomial mappings, and some miscellaneous results. And for the end of the conference, I see that will be the most important part because it will show you how this person, how good it was. It will be a little surprise. Okay? First, two words about his say that biographical data. He has been born in 65 in a little town Mira, beautiful beach, by the way, over there in the district of Coimbra. Okay, he decided to study mathematics. He have one of the highest mark, but he don't want to go to any medicine, which was very, how to say, prestigious career over there, even lawyer, and he loved mathematics. People that know him can understand why. The main reason is he was a high passion about math. Okay. In fact, when he finished, he get the special award that is in the mathematics department of Coimbra for the student with the highest mark of his promotion. Okay. When he finished, he became assistant professor. It was a typical thing over there, and he started to work in his master thesis on polinomios ortogonales y funcionales semiclásicos, more or less the same in English. He finished in 93. He finished the bachelor in 89. In 93, he defended the master thesis, and in 97, he finished the PhD. I need some preliminaries in order that you understand what he did. He works essentially in orthogonal polynomial theory. For the orthogonal polynomials, you have a polynomials, Pn, okay, let P the space of all polynomials with a complex coefficient. You say that they are orthogonal if, with respect to a functional, linear functional, if this product that you can see over there, okay, is 0 when the degrees are different and different from 0. If for a given functional the sequence of polynomials exists, then it is say that the functional is regular. Okay? A special case is when you have, for example, this representation, if you want the risk representation for the functional, but the classical one is when you get a continuous wave function, and then the orthogonality that you get is the classical one. Okay? In case that when you apply P to any positive functional, this is positive, the functional is said to be a definite positive functional. And this is one of the main areas in which Jose Carlos was working during his whole life, okay? One of his first work was about characterization, but let me tell you a little history about polynomials in less than 1 minute. The first time that orthogonal polynomials appears in the history of mathematics was in the work by Legendre, in trying to understand how an spheroid is attracting, point masses. And he found an orthogonal polynomial sequence he called now Legendre polynomials that satisfy this relation that you can see over there, okay? They satisfy also a differential equation. The solution of a linear differential equation are these polynomials, okay? Because of the orthogonality, he also proved that they satisfy the three-term recurrent relation. All this work I will use during this talk, okay? Also, the orthogonality was with respect to a wave function, as I say, this rho, what is over here, and this rho is a solution of the first order differential equation named the Pearson equation, okay? Finally, they can be obtained explicitly expression for these polynomials using this formula, usually call it the Rodriguez formula, okay? The interesting thing is that that we call now classical orthogonal polynomials, that are polynomials that are related to the names of Hermite, Laguerre, Jacobi, and Bessel. They satisfy all these kind of properties. Interesting one is that their solution of this equation their orthogonalities with respect to some wave function that satisfy these kind of things, and there's other ones that I will comment in a moment. Okay? To prove all these things, let me say that it's extremely complicated. Okay? If you take a look, for example, of the paper of Bochner, who proved that the only orthogonal polynomial solution of the second order differential equation was this fourth thing, is very complicated to get. Even almost all. It was clear that somewhere at some moment it should appear a theory that can help. And this theory, of course, was the functional analysis, okay, which is one of the topics of this conference. And in fact was Pascal Maroni, you can see him in that photo with Jose Carlos, the father of this theory. I will call that, it is called the algebraic theory of orthogonal polynomials, okay? Jose Carlos was, he was a fan, a big fan, it's the only I can say of the work of Maroni, and he really understood how it works. The main idea for the mathematician is that when you have the orthogonal, the polynomial space, the algebraic dual and the adjoint dual, if you want, are equivalent in some special, with some special topology, say that. And this allows you to use all the machinery of functional analysis on dual space and then get a lot of results in the normal space of polynomials, okay? Let me talk about the first contribution of Jose Carlos on this topic that he considered his most important one from his first period of life. This was the classical orthogonal polynomials. Essentially, the definition is that you have a regular functional, and then they satisfy a first order differential equation in the distributional equation. Okay, if you take a look to that, there's two immediate questions that appear. This equation has a non-trivial solution. Second, the functional, if you get the solution, is regular. It has some kind of orthogonal polynomial sequence. The answer to that was in a paper in '94 in Integral Transform and Special Functions. It's a very beautiful paper, okay? Summarizing, he found necessary and sufficient condition for this to happen, to answer yes to these two questions. And this is curious because if you get this differential equation, the data that you have is these two polynomials, second degree, first degree polynomials, okay? Let's write in that way, and everything that you see is that the conditions only depends on the coefficient of these two polynomials, nothing else, okay? You do not need to impose anything extra. Even from that, then you can find the coefficient of the three-term recurrent relation, which is the best way of generating the orthogonal polynomials, and also you can get a Rodriguez formula in the distributional sense. It was an amazing paper. Even say that he loved these results, okay? You can just put everything together and then you can see that this theorem gives you exactly the necessary and sufficient condition to get the non-trivial solution, give a characterization of all classical functionals, and therefore somehow classical polynomials, okay? And the condition was beautiful, okay? This is in red. It's very important because all the phi and c that you can get, you can multiply by obviously non-zero constant and you get the same solution, okay? Everything depends only on these two things. Let me say one thing more to go further, was about characterization theorems. In fact, from his first paper was not this one, it was a previous paper with Branquinho and Marcellan about characterization, but he never liked that paper. He told me several times, especially at the end of his life, that he don't like so much that paper. And I understand why. He told me, in fact, in that paper, it is assuming that the functional was regular. And of course, if you assume that, it could be that the functional was not regular, so you are assuming something that is doesn't exist. Okay? But secondly, he realized that Maroni itself had been announced this characterization in a paper in 91. It's a typical scene in the French school that they announce, and by the way, the French school, and I think also that was the Soviet, now Russian probably school, they announced the results in a little letter, say that, and after that, they wrote a big paper, say that, on that things. The Maroni's paper arrived more or less at the same time at the, say that, this paper in 93. But the other one, even Maroni was unable to prove that the functional was regular. So Jose Carlos was very proud that he did, okay? I will just mention some of the characterization, but now I will move 30 years, as you can see. This appeared in 23 in the result of mathematics very recently. For example, if you have a classical orthogonal polynomials, the name of Jacobi and so on that I told you, then this is the only one that satisfies this Pearson equation, distributional equation. By the way, this was Maroni's characterization. The second one is, for example, the Al-Salan-Chihara characterization that claim that the only sequence of orthogonal polynomials that satisfy this differential difference equation was the classical orthogonal polynomial. The Ham is related that the only orthogonal polynomial sequence that satisfy that their derivatives are also orthogonal polynomial sequence are the classical one. The C4, which by the way, several times for key equal to 1, was attributed to Marcellan, Branquinho, and Petronillo, but this was wrong because in the 1940, Hieronymus have proved this in a beautiful paper that unfortunately only it is in Russian, so a lot of people miss. But I mean, you can find, you can find in the internet. The Boxner that I told you about the differential equation and also the Rodriguez. This C4 for arbitrary key is a contribution by Jose Carlos with Kenyer in that paper. Okay? Let me say that when you take a look to the proof of this theorem, the proof is hard, okay? But if you compare with the proof, original proof for C1, C2, say that, C3, C5, or C7, you realize how powerful was the algebraic theory invented by Maroni and developed in a very beautiful way in the works of Petronillo, okay? Now I will move to his second very important contribution was about orthogonal polynomial mappings. An example, a classical example, if you have the sequence of L and H, Laguerre and Hermite polynomials, and you can see that the Hermite polynomial can be related by this Laguerre polynomial just by a chain of variables, okay? And so Jose Carlos, in his thesis, he solved this kind of problem when you have two special cases. But I will just discuss the general case that he also solved it later on. Suppose that you have a monic orthogonal polynomial sequence, fix a key less or equal than 2, and suppose that you have another orthogonal polynomial sequence. And the question is if you can find some kind of relation like this. The Pn with the proper degrees is equal to the Qn evaluated in some polynomial, that is the polynomial mapping, multiplied by some polynomials in case you need the degrees works, okay? The complete solution of that problem was done in a paper of 34 pages, which is very hard. The proofs are elegant, but yes, it's quite hard. It's a lot of things to solve. That he did with his first PhD student, De Jesus. It was published in Journal of Approximation Theory in 2010. He gets a full characterization of that problem, but also he recovered all previous results. This is one of the best contributions of Jose Carlos in the theory. He was very proud about that. Okay, as I told, he used that, I mean, obtained the result for key equal 2 and 3 in his PhD thesis in 97, but several times he told me that he was very unhappy because for the case key is equal to 2, say that the proof was not elegant from his point of view. But he found a way to solve the problem for key is equal to 3, and this give him the key for solving the full, the complete problem, okay? And he was very unhappy because the two papers he wrote in k is equal to 3, because of the suggestion of his advisor, was sent to a journal that nobody knows. And everything was based on these two. He was very unhappy, uncomfortable with that, but I should say that Jose Carlos was some kind of person so shy that he could not refuse when they get this kind of offer. Okay, that is the paper over there is this one. Okay, but in honor of the truth, I must say that 5 years before, he solved not that problem, but using almost the same theory with not the full characterization, he just able to apply this in a beautiful area of linear algebra, is the so-called the Kat-Topliss matrix. In fact, finding inverse and eigenvalues and eigenfunction. I will take a little history that happened with me and him, and that say too much not about him and about the academic world we are living over now. For example, when I came in 93 and started working in my PhD, I get the suggestion from my advisor to find an application of the Kral polynomials. I was shocked. The Kral polynomials say that are polynomials that are say that perturbation of the normal polynomial. Suppose that you have a sequence of polynomials with respect to u, okay, and then you add to the functional some kind of, say that delta theta functionals, okay? And at this time in the 90s was a lot of active area of research in orthogonal polynomials, and there he was interesting to find. I came from physics, so I suppose that I can find a physical theory. But for me it was a shock because I came from a school, the Russian school, now at that time was the Soviet school, and they taught me in a different way. You have a problem to solve, a physical problem, whatever you want, and then you find a way to solve it. If you need to invent the mathematics, you invent the mathematics. So the idea was not you have an invented theory, invented in the sense you found a theory, and then with this theory try to find an application. Well, I later understand that it's a question of selling. I was living in a, say that they call Communist Party was nothing to sell, you know? And the science, in fact, was not something that you never will say. It was forbidden, okay? Okay. What happens? After, in 94, after I think that 2 times he came and lived with us, always we have a lot of discussion because we didn't want to get money from him. He insisted, but at the end, we became more or less a little friends. The friendship was started, and since all the time he was eating with us, even go to the university with us, and so we start talking about what he's doing, what I'm doing, okay? And so in 94, he invited us to to visit him and his family in Portugal, and we spent a beautiful summer in 94. This is Jose Carlos with his little daughter, Sara, okay? It was almost 3 years old, and there we are just sitting, eating with her father, Joan, and her mother, Elena. Sara is always sitting up there, as you see. Okay, we start talking and talking and talking, and what happened? On 95 or something like that, he was sitting and tell me and explain me what he's doing with this polynomial mapping. I don't remember how. I arrived to a paper that is related with the so-called chain model. The idea is the following. Suppose that you have a quantum mechanics system, okay, and you need to find the solution of the Schrodinger equation, okay? Usually you cannot solve the Schrodinger equation analytically. I mean, the real one. So what the physics did is the following. You get an expansion on some kind of, say that complete basis in L2, then you expand this, and you get corresponding products, and then you change the differential equation somehow, or if you want this equation to a system of equations. When you get the system of the equation, it looks like that. Everything is okay. You put in a computer. Oh, but if you put in a computer and this n, capital N, is too big, the computer just blow up. You cannot solve. Okay? So there you need to find models. One of the simplest models was the so-called chain model. The chain model, the idea is there is a way of changing this huge, with non-zero matrix to a tridiagonal matrix. The tridiagonal matrices are beautiful, and since there's a tridiagonal matrix, there is direct connection with the theory of orthogonal polynomials. And from this reason, Jose Carlos started working that. Even the periodic. For example, for key is equal to 2, he completely solved the problem of finding the eigenvalue problem. He found that the eigenvalues of this matrix that I show you are essentially the solution at the zeros of some polynomial is n that is given that way. And this P is nothing else than the Chebyshev polynomial, okay? And you need to find the solution of this. Imagine that you have a matrix of, 1 million entrants. Dimension 1 million by 1 million. Nobody can solve that. But since it's a periodic, the only thing that you need to do is to solve this little second order equation, algebraic equation that is very easy to solve. Okay? So most important thing that we found, or he found, is that when you try to find the orthogonality measure, if you want the functional or the distributional function, what we see is that you have a continuous part and you have a delta. And when I saw that, I said, oh, Jose Carlos, this is a Kral type polynomial. This was the thing that I asked for to take a look. So we found an example of application that we never expected. We decided just to work more on that, and after some time, we wrote a little paper in the process. This was in the 95, in 96, we become closer and closer. This is a photo. We went together for a summer course in approximation theory in Vico Equense in the Naples Gulf Stream. It's amazing. It was in a ship, and there this was a discussion that we have with some wine, as you can see, just the day before I defend my PhD thesis in June 96. Okay? I will finish this part with a little example of what this was so interesting. If you get a real Hamiltonian like this one, this is a way that you can describe, for example, a ring of coupled oscillators. By the way, non-linear oscillators. If you have the ring, you have a periodic matrix. But if you have a chain of oscillators that also appears in a lot of applications, then you have not a periodic matrix. That we found is that you have, instead of tridiagonal matrix, you need to add at the beginning and at the end some kind of perturbation. So I was thinking how we can solve that. Of course, the only way that I can solve that is to come to Coimbra and ask Jose Carlos what we can do with that, because he knows everything about these kind of things. And we decided just to solve that problem. The first thing that we did was to discuss what is the relation between the zeros of this perturbed matrix, when this mu and lambda is 0, okay, and the one when you have these two parameters that were positive in general. Okay. If you know how they interlay, you can get more or less properties. The second one is how close they are, because it say that in applied math or applied physics, applied, science, you not only need the theory, you need to get the numbers, okay? And so mathematicians love to do everything analytically, if you can. So if I know how to solve one of the problems, in fact, I know how to solve this exactly, okay, then I can know how to solve approximately the other. How close they are, okay? The first theorem that I just showed you the idea was, okay, for this matrix, all the eigenvalues are just inside some intervals that are the inverse of the mapping of the polynomial pk, though that polynomial that appeared in the definition or in the problem of the polynomial mapping that I just showed, I don't know, 10 minutes ago. A key point is this delta polynomial that he found very useful, and he was an idea that he found in papers of Ismail and Charris, okay? And he found that everything, we found that everything is inside this interval except key minus 1 point that are separating this interval and that are exactly the key roots of these polynomials, okay? That is the good picture. You have the polynomial mappings over there. You have your interval, and you construct these three. Everything lies here, 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 and maybe you can have these two. That you have these 2 points or not depends only on the parameter of the matrix. At that time, I must to say that this was working, we were working in a European project that Luis Cardoso, who is sitting over there, me convinced him to do it because we needed a partner in Spain and a partner in Portugal. He didn't want to go, but at the end, he decided just to run for that project, and we got it, and we worked a lot on this, on these things. Also, Nurka, that was sitting over there, was working with us and helped with the numerical simulation that Jose Carlos don't want to hear any words about that, and for me, it was very complicated, okay? Let me prove one thing at the conference. The idea is the following. We went to the office of Jose Carlos and started thinking on a particular example. After get some idea or some hypothesis, we just went. It's not moving anymore. To a larger blackboard, because you see, we have not sufficient space. I start discussing, and at the end, we get the results. So time for beer. But this time, the time for beer was because you realize that somebody took the other picture. And it was Luis Cardoso that don't want to, that we continue working and just take us for a beer. Okay? That is a joke, obviously. That is the result of how close the eigenvalues were. Okay? Just take a look to the last one if you want. At the end, we get, this is the perturbed matrix. This is the one that we can find essentially in a very easy way the solution. Of course, for key is too big, no. But for 2 and 3, you can get analytically if you want. As you see, as n is bigger and bigger, you can get they're closer and closer, and so you can almost, for the application, use the not perturbed matrix, and everything goes well. I need to say that we found other interesting things, and we make a lot of numerical experiments thanks to the program that Nurka grow, and we found very curious, phenomena. And at the end, in 2000, we published some paper in 93, in 95, something like that, but this takes a lot of time, and only in 2012. We get a very nice time at this time. And to finish that, I must say a little history. I remember the first time when I come with the proof of this kind of bones, this charge bone, I used the regular perturbation theory, which is very typical theory in the mathematical, applied mathematics. And when he saw that, he refused. Say that it is very applied. I cannot do that. I can accept that the result is okay. I show the simulation and say, no. And then he starts thinking, and at the end, he arrived to the beautiful proof using elementary classical analysis. That is the way always he was thinking. To get beautiful proof in the sense, say that, or Hardy or Dirac, that say that it's a proof or the theory is not beautiful, that is not a good theory. Okay? I move forward. The next beautiful contribution of Jose Carlos was related also with the algebraic theory. I briefly comment some of the results. It is even very old thing. The first problem related with that was Hieronymus in the 1940. Suppose that you have a polynomial, orthogonal polynomial sequence Pn and another one Qn, okay? And there is a linear relation between that. This symbol means the derivative. Could be the classical derivative, could be discrete derivatives, Q derivatives, whatever you want. In this paper, in this one, it is a classical derivative, okay? And so the question is to find a relation between, if there is any relation between the functional with respect to which Pn are orthogonal and the one that the Qn are orthogonal. I mean, U is the functional with respect to which Pn are orthogonal and V to Qn, then there isn't a relation of that. He was always interested in finding this kind of problem. If you get this n, big N, equal to 0, okay, this m equal to 0, and the other one here equal to 1, and this m equal to 1, no, to 1, not to 2, then you get the Hieronymus problem, okay? And that was one of the characterizations that I told you that they, and this is somehow a generalization. He solved that in a paper, this is Hieronymus. Let me check, yes. He solved that first for very particular case in a very short paper in Journal of Mathematical Analysis. And the general case he solved with De Jesus, his student, in 2008. And he used the Maroni algebraic theory. I guess that without that you cannot solve that kind of problems, okay? But the idea was so good that he just invented, or he generalized this, and he introduced the concept of M-coherent pairs in a paper with De Jesus, okay? The idea is that you have these kind of relations, and the N and N, M and N as the number of say that, of summand that you have here and here, okay? So they prove that when M is equal to key, this is not the one that I wanted to show. Okay, in any case, I have no, I will just, they found the theory, how they're related, but also in a special case, then they prove that the functional are semi-classical. If this is semi-classical, then there was already the theory completely developed by Maroni about semi-classical polynomials. So he can use it, and you get all the problem solved. One interesting connection was that this is related, this kind of expression is related with the so-called Sobolev orthogonal polynomials. If you know how to solve this linear relation problem, say that, then you have a way of efficiently found the Sobolev orthogonal polynomials that are very interesting in numerical analysis. And the problem that Jose Carlos solved, in fact, and the connection he found with the Sobolev orthogonal polynomial was a non-trivial generalization of an already classical paper by Searles and collaborators in 91 that appeared in Journal of Approximation Theory. Okay? Finally, let me say that he generalized that. Here is the N and key that appears. Also to the Q derivative and this kind of stuff, okay? But at that time, it was around 2016, it was completely exhausted. I remember in 2016, me and my wife asked us for a sabbatical to go to Germany. I got it, and she didn't go it, so we didn't go to any place. But I traveled a little, and I come to visit one time, and of course, he he cannot say no because it was me, but he told me that he cannot work. He said, I don't need to work. We can go and take a restaurant, take a walk, talk about life or kids, whatever you want. And he told me he cannot survive anymore. He's very, 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 very tired. And I will try to explain you, but because in our life we will have good moments and bad moments. And I think that it's very important to know this also in his life. He was appointed as a associate professor in 2005. And after that, he need to pay for that. Say that, okay? There is no written rules in Coimbra that when you get associate professor, you need to spend some time with bureaucracy. And he was a member of the Bologna Commission. This means he need to understand how to transform the Portuguese system to the new European system. He did so well that the rector take him to all the meetings in Lisboa. In 2007, he was elected a member of Scientific Commission. He got a lot of work over there until he died. He was a vice president of the department from 2006 to 2009. When he seen that everything is okay, he was the vice president, also director of the department from 2013-17. And at this time, he was already, exhausted, okay? I several times told him, you need to figure out how to just relieve the stress, because you cannot live with that stress. I tried to convince just to run, to go to swimming, whatever. Even when I went to him during that period of 3 or 4 years, we take a walk and so on. I used to run, but okay. At the end of his life, somebody convinced him. It was Kenya. Kenya appears in Coimbra around, I think that at the end in 2015, I started working with him, and he convinced at the end just to go some sport. And I was very happy, but maybe it was too late, I don't know, okay? In 2018, he decided to apply for aggregation, for habilitation. At the end, he was thinking several times, as usual, but at the end, he decided to go, okay? And he got it. After that, was when he finished all these things, of this bureaucratic thing, he has been reborn from the mathematical point of view. I think that probably Kenny helped a lot because it's a young postdoc arrived with strengths, he wanted to work, and he took Jose Carlos, and at the end, he started working. And I was just told very little because I have not much time. What was one of his last contribution that, by the way, he think was his better contribution, was the idea of Kenner was try to put together the theory of Maroni and the theory of Nikiforov Uvarov of orthogonal polynomials. Jose Carlos knew perfectly the first one. The second one he knew more or less because I explained several times. I was educated on that school and with Nikiforov. And the idea is you have the differential equation, you use, say that, an approximation scheme, for example, in uniform lattice, and then you transform this into the difference equation and work with that. Numerically, you can do this in a very easy way. But what Nikiforov and Uvarov really did is they realized that you can do in any lattice, nonlinear lattice. In fact, they show that it's sufficient to use this kind of lattice. This is very interesting because the first lattice that you see with this Q over there, this is the typical lattice for the Askey-Wilson polynomial. The second one is for the Wilson polynomials or Racah polynomials. All the theories you can find in the book of Nikiforov and Uvarov. The first one is the Russian edition of the special function of mathematical physics. The second one was the English translation of the discrete case, say that he grow, they grow. At that time, they invite me to work with, he invited me to work with his new team, which was Kenyer and the new student that they have is sitting over there, Dieudonné, and we solved the problem, the characterization problem of classical functional, but for the Ham operator, okay? In 1907, I went again there. He invited me to give a talk and to discuss for the next project. He was quite happy, work a lot. You can see the blackboard is full of. We get dinner with some friends. In there you can see one of the oldest full professor, catedrático in Coimbra, Jose Victoria, that was a close friend of him. It is important to mention. He was happy. He took me to some excursion. Let's go to Porto with Celia, and the other one was Figueira da Foz to see the sea, to talk. We talk a lot. We work a lot, but especially we talk a lot. Okay? And start working in our thing. I mean, that is the main theorem that they prove. At the same time, with Kenyer and Dieudonné, after a lot of work, he showed me the paper before sending to any place. It was an amazing paper when they say that they did what he started in 93, and he classified all the functional that are regular but on lattices. And he recovered the ASCII Wilson, all these kind of things. It was a beautiful, I get some envy. Oh, he really did a beautiful work, and I was very happy. He was also very happy. But at that time, already he have a big problem with sleeping. I remember a lot of discussion that we have together with Celia, even Luis Cardoso tried to explain because he have also some little problem with sleeping. Okay? I am just coming to the end of my talk. So the papers appeared in 2002 after being rejected in two journals, in Journal of Country's Approximation and the Proceedings, and he was very upset because he have a lot of rejection with unfair referee report. And this has also history with a person sitting over here, because this was also rejected in Journal of Mathematical Analysis and Applications. And I know that after Jose Carlos' death, they got, Kenner showed me a report was awful, and then he just sent an email to Aaron, Richard and Aaron, this is over there, and Aaron realized that he was very unfair and just asked the editor just to sing about what they are doing, and finally it was accepted, but Jose Carlos could not see his most important work just published because he died before. Okay, to finishing, it will be appear now a book. The history of the book is very complicated. I will not spend 5 minutes on that, in which everything, all this algebraic theory is put in a beautiful way. It was an idea of working with by Kenner and by Pascal Maroni with Kenner, but Kenner say that Jose Carlos should be there, and at the end, only Jose Carlos and Kenner did, and will be appear right now. It's an amazing book. It's a real gem. Okay, we start just the last time when I was in 1920. I come to Coimbra for the last time. I never knew that was my last time up to now. We again gone to Jose Victoria, to some places. We were at home. You can see over Kenyer, the Jose Carlos' daughter Inés, that will become, I think that on Wednesday probably. He was very happy. You can see his face. We all were very happy because he's not the sad person that I remember from 2016. But then there is something that happened. And just to finish, I must to say two things. The first, I cannot cover all his work. I cannot cover the work he did with his very good friend Luis. Okay, we were tried every time to get a work together, but it was impossible for several reasons. Okay, in fact, this photo we are three over there was in a cool day when we finished to prove that theorem on matrices, and then went to beer. Okay, just to finish this talk, I would like to ask my kids to come to the stage, because I have a little surprise, and I will finish this talk in 5 minutes, please. Let me just finish with as I promised, in the same way I began. Okay. Um, I only knew that Jose Carlos was in the hospital the day he died. There was some kind of strange thing that happened, but the next day was a Saturday, and this Saturday, 2027, around 2 p.m., my phone started just ringing all the time. So several people just the camera just need go to them, please. Some of the people called me, but one of them was especially sad. I mean, Jose Victoria just phoned and asked me if I know the news. I said that I know the bad news. And he started just saying, the only word that he could say, es tan triste, Renato. It's so sad. All the time I'm finished. Then, when I come home, my wife asked, we were in a park with a relative that came from Madrid to visit us, okay? And when they arrived, we was all the time just drinking a beer. Where there was summer, August in Sevilla. Some people can, if you don't know, I can show you, it's hell, okay, over there. In the afternoon, my wife asked, what is happening with Jose Carlos? I say, oh, it happened that, I say, Sophia is asking. I tried that nobody here. I left. Well, I was in a park. I was far away, but Sophia is here. And then on Sunday, I just we have a special lunch. Then I opened my best Porto wine, a vintage, but almost sure that was him or Luis. And then explained the situation and so on. But then few days later, I came to the Sophia's and she told me, what are you doing, Sophia? And she said, I am writing a song. What I seen that day can explain better.
Hi everyone, we are Sofia and Renato, and we are going to perform a song that we wrote in the memory of Jose Carlos. We wrote it some time ago, so it's a simple song. It's a bit childish, I think, but I don't know. We kind of like it, and well, it's in the memory of a truly wonderful person. So I hope you like it.
Oh, my friend, you've gone away. You've taken that trip and I won't see you again. But it doesn't matter, I still have you here inside of me. I knew you were going to go someday, though I wasn't expecting it for it to be so soon. I thought we had time left, but I remember you, I remember you as the person who made me smile, as the person who taught me that 2 + 2 = 3, a person who I aspire to be. Oh, my friend, you had a hard life, and it's difficult to realize I won't hear you again, but it's alright. Oh, my friend, you've gone away, but in my mind I'll remember you as the great person you were. Doesn't matter if I don't feel you no more, 'cause I'll meet you again on my sweet dreams. I'll listen to your voice inside my heart. I've known you, and that's all that matters. That's all that matters. All that matters. All that matters to me. Oh, my friend, I'll think of you again. Doesn't matter how soon you left. What matters is how long I'll remember you, and I promise I'll remember you. You tried so hard. What a brilliant mind. I won't let the memory of you fade away. I'll remember, I'll remember, I'll remember you, my friend.
That's all.